Download this code and get free GPT-4o from codegive.com, link in the description below. Keras is a powerful and popular deep learning library that allows for easy and fast experimentation with neural networks. When combined with the Cuda toolkit, Keras can leverage the computational power of nvidia GPUs, significantly speeding up the training and inference processes. Here's an informative tutorial on how to set up and use Keras with the Cuda toolkit. Prerequisites. 1. nvidia GPU. Ensure you have an nvidia GPU installed on your machine. 2. nvidia driver. Install the latest nvidia driver for your GPU. 3. Cuda toolkit. Download and install the Cuda toolkit from the nvidia website, https://developer.nvidia.com/cuda-downloads. 4. CUDNN. Download and install CUDNN, Cuda Deep Neural Network Library, from the nvidia website, https://developer.nvidia.com/cudnn. Step 1, install TensorFlow with GPU support. Keras is now part of TensorFlow, so when you install TensorFlow, you also get Keras. Make sure to install the version that supports GPU. Bash. Pip install TensorFlow. Make sure to install the TensorFlow-gpu version if you are using an older TensorFlow version, before 2.0. However, from TensorFlow 2.0 onward, the TensorFlow package automatically supports GPU if available. Step 2, verify GPU installation. You can verify whether TensorFlow is using your GPU by running the following code in a Python environment. Python. Import TensorFlow stf. Check if GPU is available. Print, number GPUs available, len, tf.config.list_physical_devices, GPU. If everything is set up correctly, this code should return the number of available GPUs. Step 3, basic Keras model example. Now that you have Keras and Cuda set up, you can start building a simple neural network. Below is a complete example using the Keras API to create and train a simple neural network on the NIST dataset. Python. Import TensorFlow stf. From TensorFlow import Keras. From TensorFlow.Keras import layers. Import NumPy as np. Load the NIST dataset. NIST equals keras.datasets.nist. x_train, y_train, x_test, y_test, equals nist.load_data. Normalize the pixel values to be between 0 and 1. x_train equals x_train.astype, float 32/255. x_test equals x_test.astype, float 32/255. Reshape the data to number_samples 28, 1 for CNN. x_train equals np.expend_dims, x_train, -1. x_test equals np.expend_dims, x_test, -1. Create a simple CNN model. Model equals keras.sequential. Layers.conv2d, 32/3 activation equals relug, input_shape equals 28, 1. Layers.maxpooling2d, 2. Layers.conv2d, 64/3 activation equals relug. Layers.maxpooling2d, 2. Layers.flatten. Layers.dense, 64, activation equals relug. Layers.dense, 10, activation equals softmax. Hashtag compile the model. Model.compile, optimizer equals atom. Loss equals sparse _ categorical _ cross entropy. Metrics equals accuracy. Hashtag train the model. Model.fit, x _ train, y _ train, epochs equals 5, batch _ size equals 64, validation _ split equals 0.1. Hashtag evaluate the model. Test _ loss, test _ acc equals model.evaluate, x _ test, y _ test, verbose equals 2. Print, \n test accuracy, test _ acc. Hashtag explanation of the code. 1. Data loading and pre-processing. The NIST dataset is loaded. It consists of 28 x 28 pixel images of handwritten digits. The pixel values are normalized to be in the range 0, 1. 2. Model definition. A simple convolutional neural network, CNN, is defined using the Keras sequential API. The model consists of 2 convolutional layers followed by max pooling, and finally 2 dense layers. 3. Compilation. The model is compiled with the atom optimizer and sparse categorical cross-entropy loss function. 4. Training. The model is trained for 5 epochs with a batch size of 64. 5. Evaluation. The model is evaluated on the test set, and the accuracy is printed. Step 4, additional tips. Monitor GPU usage. You can monitor GPU usage using tools like nvidia SME in the terminal. Adjust batch size. Depending on your GPU memory, you may need to adjust the batch size to prevent out-of-memory errors. Experiment with model architectures. Feel free to modify the model architecture, learning rate, and number of epochs to improve performance. Conclusion. This tutorial provides a foundational understanding of using Keras with the Cuda toolkit for GPU acceleration. By following these steps and utilizing the example code, you can start building and training deep learning models more efficiently. Happy coding!